Hi, hello everyone, good morning. My name is Omar Rodriguez Rivero and I am a PhD student at the Escuela Superior de Física y Matemáticas of the Instituto Politécnico Nacional in Mexico. Today, I'm pleased to present our work entitled Synthesis of Activate Carbon Fiber from Cotton Fiber under Evaluation by ATR-IR Spectra and Scanning Electron Microscopy. As introduction, as we know, the activate carbon fiber have aroused great interest in environmental application due to their high surface area, porosity, and absorption capacity. The transformation of the natural fibers such as a cotton into a functional carbonaceous material represent a sustainable and a low-cost alternative. That is the purpose of this work. How to start this? Through a chemical and thermal treatment that is possible to modify the structure and composition of the material to improve it at adsorption properties, particularly in the removal of contaminants such as heavy metals in the wastewater, uh, uh, for example, lead or cadmium or, or different heavy metals. As an objective, synthesize activate carbon fiber from a cotton fibers by a controlled chemical process and evaluate their structural, chemical, and morphological evolution in order to determine their potential as a lead adsorption material. In another work, it's like filters. Filters that we use in the wastewater to remove some of different heavy metals. In this case, just work in lead. That is the ion that we worked. Well, we get a different microscopy obtained after the process of every one of sample. And well, we observe a natural cotton fiber, continue with mercerized cotton fiber, and appreciate the surface starting to change. Continue with stabilized cotton fiber and the activation with sulfuric acid by 5%, right? And activate carbon fiber after to use a removal in aqueous solution of a lead nitrate. Appreciate this micrography using an acceleration voltage of 1 kiloelectron volt. Well, all of this imagine using secondary electron and just the final we work or we use it and backscattering electrons. Why? Because we need to we try to observe or to represent our evidence uh, by the contrast or different contrast by the atomic weight of the different compounds. In this case, the this part that are a lot of bright or maybe are in the white color corresponding to particles or lead. And well, the fiber is still be fiber. And continue with this spectra IR. Well, here obtain an ATR-AR spectra obtained from the different cotton fibers through the process. For example, we get the natural cotton fiber in color black, mercerized cotton fiber, stabilize, activate cotton fiber, and finally, the activate carbon fiber with lead nitrate. Well, we appreciate a different change it through the process corresponding to hydroxyl groups. For example, three strong bands are observed here, which correspond to hydroxyl groups, like here. These three in color blue, and we appreciate this band, this intensity of energy is starting to, to disappear through this process. All right. Nevertheless, bound stretch, carbonyl, they are observed as intense peaks in this area. This corresponding two lines of color green, corresponding and stretching, an aromatic stretching and flexing oxygen with hydrogen. And well, that is the another 6 lines or another 6 peaks or signal or bands of energy that corresponding to a fingerprint corresponding to the cellulose material. All right. Well, as we fiber starting to change the morphological through this process, finally obtain and activate carbon fiber, we appreciate the hydroxyl group, this completely disappear, but the carbonyl groups starting with more intensity. That suggests that we, how do you say? Mm, okay, this behavior indicates the hydration and deoxygenation reaction during this process of mercerization, stabilize, and activate with sulfuric acid, leading to a more ordered carbon structure with a lower surface polarity. Okay. Uh, to final or in a conclusion, the as we know in these results, the activate carbon fibers obtained in this work exhibit a promising structural and surface characteristic for environmental application, and the combination of ATR IR spectra and scanning electron microscopy confirms both the chemical modification of the cellulose and the preservation of the fibrous morphology after activation. And these characteristics suggest that the activate carbon fiber derived from cotton fiber are a sustainable, low-cost, and efficient alternative for the removal of heavy metals, particularly in this case, lead. And well, we get some of the table 1 of contain the assignment of each vibration band with representative wave number and functional groups. For example, hydroxyl groups, for example, glycosidic bonds, for example, linked beta-glycosidic in cellulose. Well, that is a spectra show the vibration bands corresponding to a carbonyl function groups, carbon without oxygen. Yes, here, for example. While the absence of the characteristical signal of hydroxyl groups confirm, like this, or like here, confirms their elimination after the process of mercerization and chemical stabilization. For example, in this image. Well, on the other hand, the scanning electron microscopy images show that the original fibrous morphology of cotton is preserved after activation, although with more homogeneous compact surface and with less roughness compared to untreated fibers, which present great structural heterogeneity. For example, here that is the first one, the mercerized cotton fiber, stabilize, activation with the activate carbon fiber after removal in aqueous solution with lead nitrate, and well, that is the compared to intensity, no? Well, thank you very much for your attention, and I will be happy to answer any question, and see you soon. Take care and goodbye.